Hello everyone, I'm Mr. Furlong, and today we're talking fossils. That's right, we're looking at fossils today, in particular the fossil record. So to start us off, paleontologists are scientists who study fossils. And we can use fossils for a whole bunch of different things. For instance, we can use this to study evolution. By using fossils, we can see how organisms have changed over time. We can use this to look at paleoecology. So all that's a nice fancy word, which means we can take a look at what were the ecosystems like in the past. The Earth wasn't always like it is now. It was very different over the 4.5 billion years. So the fossil record can tell us what types of plants and animals lived during those times. We can use it to reconstruct the history of the Earth. For instance, we know that organisms of today, they weren't around in the past. We don't see fossils of them. And organisms that we find fossils of in the past, they're not around today. Now, contrary to popular belief, fossils are found all over the place. Here we see the Falls of Ohio State Park, that's in Kentucky, I believe. And you see a picture of the Ohio River, and in the diversion process, they found this bedrock that was just filled with fossils. Here are some examples of fossils that were discovered there. Here's an artist's rendition of what these organisms look like. Some of them are similar to species that we have today, and some of them might look quite different. And these are examples of some imprinted fossils. For instance, one of my favorite fossils that I have is my fish. This is a 58 million year old fossil. So this is an imprint of the fish, as well as here's a leaf that I have. But fossils can take all different types of things. For instance, this is my oldest fossil that I have. I don't know if you can see that or not. This is a trilobite. So this is about 530 million years old. And if you remember Jurassic Park, yeah, I don't know. Get a close-up view of that. This is an insect. There's a mosquito trapped in amber. And actually, not only is there a mosquito in here, but there is a termite as well. And these are only about 25 million years old. So I got a little double bonus with that purchase. So one of the things that we can use fossils for is to date Earth's history. And so there's different types of things. So there are different ways we can date history. One is what's called relative dating. In relative dating, we're not getting an actual number or age of the fossil, but what we're doing is we're determining which fossils are older and younger by comparing where it's found in the rock layers. So, for example, here's some sedimentary rock, which is the type of rock that we would find fossils in, and you can see the different layers. And let's label these. Let's say that there was a fossil found in layer A, layer B, and layer C. Now, this is an undisturbed area, so what we can say, because of the law of superposition that says rocks further from the surface are older than rocks closer to the surface, which means the farther down you go, the older the rock is. And so we would say that C is the oldest fossil, A is the youngest fossil. We could say that B is younger than C, but it's older than A. So notice we're not giving it age, we're simply saying which species is older than which. Now, this can come in very handy when you're studying fossils in places like the Grand Canyon, where you can see multiple different layers of rock. And because it's been relatively undisturbed over the millions of years, the farther down you go in the canyon, the older the rock is, and you can see an actual change in the fossil record. Another way that you can date fossils is by using guide fossils. So these guide fossils are short-lived but widespread organisms of a particular time period. So these would have been organisms that lived all throughout the planet, but they didn't live very long, so we don't see them in multiple different layers of rock. And so that can give us an approximate age. So we're going to be practicing doing this in one of our labs, where if we are given a set of guide fossils, we can determine approximately how old they are. So let's look at this example. Here we see our correlation of rocks with the guide fossils. We have an approximate age. So if we look at this rock layer, we see some guide fossils here, and we would simply match it up with our correlation of rocks. So we would say, oh, that's about 50 million years old. So we take a look at the next layer, and we see, well, that's about 43 million years old. And we take a look at the next layer, that's about 40 million years old. and this is 31 million years old. Now these are the guide fossils that are shown, but let's say that there was another fossil here of some creature. If it's found in this rock layer, we could estimate its age to be about 31 million years old, or at least somewhere between 30 and 40 million years old. So it's fairly simple to use these guide fossils. If you want to get an actual number, however, you might use radiometric dating. This measures the amount of radioactive elements in a rock, and we use something called the half-life to determine that age. So there you can see the formula for the half-life. Don't worry about having to use that, but you should be able to graph the data. And that's very simple to do. Every radioactive element has different half-lives. Now you may have heard of carbon dating. This uses a radioactive carbon element called carbon-14 that has a half-life of 5,730 years. Uranium-235 is much longer at a half-life of 704 million years, and potassium-40 has a half-life of 1.2 billion years. Let's use that uranium-235 as an example. In new rock that is formed, 100% of all of the uranium-235 is present. 704 million years later, half of it's gone. And so that time in years, I changed that to billion, so that's 0.7 billion years. Another 0.7 billion years goes by, and half of that is gone, so only 25% of what was originally there remains. Another 0.7 billion years goes by, half of that is going to be decayed, and so now we're down to 12.5% and so on. So if we graph that, we want to put time on the x-axis, and we're going to put the percent remaining on the y. 0 will go up by 10% each time. And let's make each one of these times, this is going to be in billion years. So let's go by 0.25, so that's going to be 1 billion, 2 billion, 3 billion. So in uranium-235, when it's first formed, it has all of the radioactive elements. In 0.7 billion years, it's going to lose half of that. So that's going to be right about here. Another 0.7 billion years goes by, so that's 1.4. It's going to be down to 25%. Another 0.7 billion years, or about 2.1, it's going to be down to 12.5%. And another 0.7 billion years is going to be down to about 2.8 billion, and it's going to be around 6.5%. Connect your dots. Now what can I do with this? Well, let's say that we found a fossil and it's in some rock that contains uranium-235, and we go to measure how much of it is still there. Let's say 30% remains. So we find 30% on our y-axis. I'm going to read over until I hit my line, and then I can read down, and then I can say, well, that's about 1 billion years old. So any of the fossils found in that rock layer would all be about 1 billion years old. But let's say there's another radioactive element in there. We could do the same thing, and we can match these up to see, are the numbers the same? Are they different? Are we going to get a range of numbers? So oftentimes you might see scientists say, well, this species is about 100 to 200 million years old. Well, that's a long period of time, but they're probably using 2 different radioactive isotopes to come up with that number. So we're going to be doing an activity on the fossil record, and you get a chance to actually use some of these real fossils in class. And I'll see you then.